I'm pleased to introduce Zygmunt Pizlo, Professor of Psychology at Purdue University. His research focus is on the cognitive process involved in perception, navigation, problem solving, and developing computational models of these mechanisms. Today, he will present a talk titled Robot Applications Might Be the Key to Understanding the Human Mind. Please take a moment to silence all electronic devices. Thank you and enjoy.
Well, thanks, it's great to be here. I wanted to thank my collaborators, Yunfeng Li, Tadamasa Sawada, and Bob Steinman. I would like to also acknowledge Bob's help in discussing the issues behind this talk. So, the starting point. About a half a century ago, the AI community decided to move away from cognitive psychology and went on to develop independently. So, it should not come as a surprise that AI researchers actually know next to nothing about human intelligence, unless you count some anecdotes in our popular press or introspections. To tell the truth, to be frank, we psychologists don't know much more about human intelligence either, because we also have not studied it. Human intelligence is hard to study. So let me give you a couple of examples and then we will elaborate. If you want to study creative thinking of such people like Einstein, you may actually have to be as smart as he was. At the very least, you must really understand exactly what he accomplished. Quite possibly, this requirement may explain why the best treatment so far of mathematical problem solving in humans can be found in books written by Polya, who was a mathematics, not psychology professor. Human intelligence is so hard that one can only wonder whether any robot can ever learn how to solve math problems or learn how to formulate new theories in physics, as smart people often can. So what kind of problems must be solved when we talk about intelligence? We still don't know how students of mathematics actually solve problems like geometry problems. This shows that psychologists do not have a theory of HI, at least in this case. Existing robots, unlike math students, cannot solve such problems at all. This shows that AI researchers do not have a theory for solving such problems either. The current algorithms can perform fast searches, but they are not creative. If we had a hunch, or we could call it hypothesis, about how students solve problems in geometry, we could test it by implementing the hypothesis in a robot. And this would be a theme for the rest of the talk. So I will give you a couple of my favorite examples from Polya book. Try to inscribe a square in a triangle so that the top corners touch the sides. Slightly more difficult, construct the triangle given the perimeter, one altitude and one angle. By the time you solve the problems, or if someone actually shows you how to solve them, you will appreciate better what I'm talking about when I say that solving problems is not easy. I cannot see how IBM Watson or Deep Blue or the algorithm for trading stocks could even begin to solve these problems, and note that two-dimensional geometry is much easier than three-dimensional. So are we at the dawn or near doom? So good math students are obviously very smart, but we have absolutely no idea how their minds work, nor how to design a robot that could emulate these students' performance. Given these facts, how can any AI researcher be prepared or even qualified to say when, if ever, robots will become smarter than human beings? They are far behind us now. Sadly, psychologists can only help a little because we have just barely scratched the surface of HI ourselves. But when you talk about solving problems, actually the issue is slightly bigger than just solving the problem that I gave you. Many problems we regularly solve seem to be impossible. For example, recovering 3D shape from a single two-dimensional image. I will give you some more examples a little later. How will a robot know which problems to attempt to solve and which ones are impossible? Also, once a robot does solve a problem, how will it know whether to keep trying to improve the solution or when to stop? At this point, the only way to answer such questions is to compare robots' performance to human beings. Note well that in order to do such a comparison, we should have a theory of human intelligence. So how I see the role of computational and robotic modeling. The human mind is a complex, nonlinear system. It follows that any piecemeal study using simple artificial inputs may tell us almost nothing about how the mind handles complex natural scenes. Emulating the human mind in computational and robotic models is arguably the best, perhaps even the only way to understand and explain the human mind. This idea is neither new nor mind. The three psychologists in 1960 in the influential book, when they were discussing the role of modeling in cognitive psychology, they said that creation of a model is a proof of clarity of your vision. If you understand how things work well enough to build your own, then your understanding must be nearly perfect. Richard Feynman, the Nobel Prize physicist, said, "What I cannot create, I don't understand." So the relation between AI and HI must be an active two-way street. The intelligence of robots produced by AI must be evaluated by comparing it to what we know about human intelligence. And if we want to make progress in our understanding of human intelligence, we need to emulate it in a robot. With this said, I will now describe two problems humans solve by using their special kind of intelligence. The first example would be recovering three-dimensional shapes from a single two-dimensional image, and the second example would be finding objects in images and recovering the structure of three-dimensional scenes. Note that computer vision has traditionally been considered the most advanced specialty in AI. So, if computer vision lags behind human vision, AI lags behind HI. So, what's the nature of the problem of three-dimensional shape perception? When you look at the box, three-dimensional object, the box is three-dimensional, but your retinal image, which is represented here by this picture, is two-dimensional, yet we see things in three dimensions. There are always infinitely many three-dimensional interpretations that can produce any given image, and you can see it by just imagining that you can move the points along the projecting lines any way you want, and the retinal image will stay the same. So how does the brain choose one three-dimensional percept, not to mention how it manages to choose the correct one? Could it be familiarity with the objects? I will show you a demo in a second, but let me first say that in this case, in the case of our cube, the most symmetrical three-dimensional interpretation of the 2D image of a cube is actually a cube. So in this example, symmetry will lead to veridical or accurate interpretation. Technically, we assume that the visual system minimized the cost function that evaluated departures from symmetry. And here one of those demos, it's called Ames chair demo. Let me change its size a little bit. So here you see a chair, but actually there is no chair out there. If I rotate this object, you see that it is like a mess out there, a bunch of rods and one parallelogram. But they are not completely random. They are arranged in three-dimensional space in such a way that when you put your eye one particular viewing point, the image produced by this mess out there will be an image of a chair, and then you see a chair. In this case, we can explain your percept by assuming that your visual system is choosing the most symmetrical three-dimensional interpretation. And this is the correct, this is the interpretation of a chair would be the interpretation that you get. But the fact that we can always arrange the elements out there in some particular different arrangements by keeping the image the same illustrates this other claim that a single image determines more than one possible three-dimensional interpretation. So let's go back to our slides. Question is, if symmetry worked very well for a cube and a chair, whether it will work for anything else. And the answer is probably will, because symmetry is quite universal in natural environment. Animals are symmetrical because of the way they move. If our body was not symmetrical, it would be hard to run along a straight line. The same with birds, fish, dogs, and so on. All animals, almost all animals, are mirror symmetrical because if you want to accomplish effective locomotion, this is how you want things to be. Plants are not necessarily mirror symmetrical, but they have other types of symmetries because of the way how they grow. Man-made objects are symmetrical because of the functions they serve. Completely asymmetrical object would be dysfunctional. It follows that symmetry is a natural shape prior, and as we say in technical parlance, you can also say a priori constraint or predilection. What I mean is that if the retinal image allows you to see symmetrical 3D object, you will see such an object. And symmetry is useful because it's very effective computationally. It allows you to recover 3D shapes of objects. Now, symmetry is not the only prior, not the only predilection that is used by the visual system, but it's probably the most important one. Before I tell you about a few other predilections of the visual system, I will say a few words about the nature of those predilections. A priori constraints that are applied to a few abstract characteristics of 3D objects like symmetry are much more effective than priors learned from experience with concrete objects. It's not even clear how you would actually learn priors for all objects out there. Note also that abstract constraints can be applied in real time and they can be applied to unfamiliar objects. So as long as you are using symmetry predilection, if I show you an image of a completely unfamiliar object, you may actually be able to see the object correctly, even though you have never seen it before. Furthermore, a priori constraints such as symmetry are mathematical concepts. They need not be derived from experience and need not be updated. We are most likely to be born with them. Symmetry is prominent in everything that lives, your brain, your DNA, you name it. So what are the additional effective shape constraints or predilections? I will show you a few. So I already described symmetry, but I will show you an example. So this is an object which actually is 1/2 of a symmetrical object. And by rotating it, I am showing you that this is 1/2. But when you look at it from the original image, actually you've quite possibly see a symmetrical object because this original image allowed for such an interpretation. The next one is the constraint or planarity. This looks like an ordinary object with planar faces, but actually each face is twisted, as you can appreciate when I rotate this object. But from the original viewing image, there was not enough evidence to tell you that the faces are not planar, so you see the planar ones, even though the non-planar were possible. And the third constraint, compactness, looks like an ordinary box, cube, except that it doesn't have to be. It could be a long rod. But from the original image, there was just not enough evidence to decide whether it is a long rod or a cube. Your brain has a predilection towards an object with maximal volume for a given surface area. For those of you who want to see some equation, this is the formal definition of compactness. Maximizing this ratio will actually explain what I just saw. But there is more to it. Here you see two unrelated lines, but if I start rotating them in 3 dimensions, you see that they are symmetrical in 3 dimensions. But in the original image, several line segments projected to the same line, we call it degenerate view. There was just not enough evidence in the image to tell you that the line is more complex, so you don't see the more complex line, even though it could have produced symmetrical interpretation. All these priors apply to abstract characteristics of objects and not to objects themselves. And so these priors don't have to be learned or updated through experience. In fact, that's good because no physical objects out there are perfectly compact or perfectly planar or perfectly symmetrical. So it may actually be hard to derive the concept of symmetry by collecting experience from multiple objects. So let's look at the demo illustrating how well our model, based on these four constraints, can recover three-dimensional shapes. So here we took a synthetic object. On the bottom left, you see a 3D model of a truck. Here we took a single image of this model. Here we drew by hand visible contours, only the visible ones. Then we applied the magic I just described, and the model is able to recover what you see on the bottom right, which is pretty much quite accurate 3D shape of the original truck, including the back invisible faces. So it is computationally possible to recover the three-dimensional structure of visible faces, but also the faces which are on the back and are not visible. Let's look at a couple of other examples. This will work with objects like this. Again, we have 3D model of a bird, one picture. We extract some lines, and just by maximizing the symmetry, and in this case, the compactness of the convex hull, containing the contours, for those of you who remember what convex hull is, for those who don't, never mind, this magic works. And you can actually check the details in our papers. Let's take this is actually on the top left, is a real photo of a real praying mantis. We asked one of the students to draw contours that he thought were important, and then by maximizing the symmetry and compactness, we are able to the model is able to recover this three-dimensional configuration of edges, which looks like close to perfect. So this is what the model can do. The question is whether this approach can recover shapes which are not necessarily symmetrical, and the answer is yes. As long as you can define how the asymmetrical object is related to symmetry, you can do it. So let me show you right away the second example. The human body is symmetrical in principle, but not in this particular configuration and articulation of hands and legs. So we can mark skeleton, which would be the edges representing the parts of the body. And when we apply to what I just described with some slight front-end modification, this is what we are going to get. So you can recover the shape of an object which is not necessarily symmetrical, as long as you can sneak in the symmetry predilection if you realize how your asymmetrical object actually could be related in 3 dimensions to symmetrical. And everyone would agree that if I give you this picture and if I ask you, how should I move the hands and legs to produce perfectly symmetrical 3-dimensional configuration, this would be an easy task to do. So often when we see objects which are not perfectly symmetrical, we right away know how they are related to the closest symmetrical object. I just showed you how the human mind, the visual part of the human mind, solves what seemed to be an insoluble problem, namely recovering a 3D shape from a single 2-dimensional image. There is good reason to believe that the computer vision community would have never even tried to solve this problem if they didn't have an existence proof of biological vision. So anyway, what do we know about the current 3-dimensional vision in robots? Well, the last 20 years of computer and robot vision was essentially doing something like a sidetrack. They didn't try to solve the 3-dimensional problem. They assumed that everything can be done by taking 2-dimensional images and producing 2-dimensional interpretations. The AI community obviously knows that there is a 3-dimensional symmetry prior, but they insist on not using it because they want the robots to be more general than we humans are. Robots should not be restricted in any way but what might prove to be unnecessary priors or constraints. But without 3-dimensional priors, there cannot be 3D vision as we know it. In other words, single 2-dimensional image always specifies infinitely many possible interpretations. And by now we know that no matter how much more data you gather, you can never produce very good 3-dimensional interpretations. But the symmetry prior, together with the other ones, will do nearly perfect job. So the conclusion is that there simply isn't a more intelligent way to see than the way we humans do it. Again, this is a conjecture. It will take some time before we convince ourselves whether it is true or not. But the human visual system is so good compared to all the methods that have been tried during the last 70 years that it is quite possible that this conjecture is true. We did put those algorithms in our robot. You can see the robot here. It is actually looks like a vacuum cleaner with a stick and a camera. The name of the robot is Chapek. After the talk, there will be a quiz why the robot's name should be Chapek. And the task of the robot is to look around and figure out what's in front of him. The first step to find objects in two-dimensional images is to actually make sense of the input. The human retina has 6 million cones, the receptors, which provide input under normal viewing conditions. This surface is actually similar to what we use in camera images. It essentially says that it's like 2,000 by 3,000 pixels. Making sense of such an image boils down to analyzing partitions of the image, and I will say a few more words what partition is, but for people who have some computer science background, they will recognize that interpreting an image will simply be represented as a combinatorial optimization problem. In psychology, we call it figure ground organization. You want to know where the objects are, and the rest of the scene is background. One example is here. If you see 5 pieces of furniture in the center of a dance floor, you successfully solved figure ground organization problem. But these kind of images actually pose a serious challenge for existing computer vision and robot vision algorithms. Real images cannot really be handled reliably by any of the existing robot vision systems. Robots typically are trained on thousands of two-dimensional images, after which they try to detect what they just saw. The robot's performance is always poor, very far from perfect, and it almost never generalizes to unfamiliar categories of objects. Besides, because the robot's visual interpretation of the three-dimensional world is two-dimensional, the robot would surely claim that the Earth is flat if you let it speak its mind. This might seem a bit odd in the 21st century. There's no reason to assume that these robots will become smarter than we are anytime soon. So, we want to solve the figure ground problem without any training. If we exclude familiarity with objects and scenes, the visual system must use some abstract rules to figure out what's the unique and correct interpretation. A brute force approach would call for examining all organizations or a large fraction of them and choosing a single one based on some well-crafted criterion. Finding the criterion may be a challenge in the first place, but what I'm saying, even if you know what's the criterion for the best interpretation, there will be just very many interpretations to try. So let's see what partition means. If your camera had only 5 pixels, then there would be 52 possible interpretations, partitions. We call number of partitions a Bell number. So what would be a Bell number for cameras with more than 5 pixels? For 10 pixels, the number of possible interpretations is 100,000. For 100 pixels, it's larger than 10 to the power 100. Now, 10 to the power 100 is larger than the number of atoms in the entire universe. Now, how much vision can you have with 100 pixels or 100 receptors? You would have some, but not a lot. My example here is that 100 receptors is in the central 3 by 3 minute of arc region of your retina, which is the size of your fingernail viewed from 10-meter distance. So it's really a tiny fraction on the image. Yet the number of interpretations of this tiny part of your camera or retinal image is 10 to the power 100. You cannot evaluate even a tiny portion of these partitions. But remember, human retina has 6 million cones, not 100. This means that the number of partitions of the retinal image is greater than 10 to the power 6 million. So it is like 1 with 6 million zeros. If you were able to evaluate 1 billion partitions each second and you started at the Big Bang As of today, you would have checked only 10 to power 26. It's a long way to go to 10 to power 6 million. So figure ground is more difficult than playing chess. And it would not help much if your computations were 1 billion faster than what I assumed. It wouldn't change too much the success in checking the partitions. So the very first step towards understanding the sensory input to the visual system presents what looks like an impossible problem. Effective biological vision is the only proof we have that this problem can be solved. The next few slides will illustrate some important and unexpected characteristics of this solution. So this is what we set up as a goal. I think the images don't look that bad. So if our robot Čapek takes a pair of images from his camera, so it is like the two eyes of several objects in the scene, the first task is to understand first of all, figure out how many objects there are. So we'd like to be able to find the objects in the three-dimensional space. And here, one way to illustrate how good the reconstruction of the scene is to place the objects on the floor. This is like a top view of the scene, but the top view is computed from those two images. And in this top view, we would hope that our robot would be able to estimate the position of the objects on the floor, the sizes and orientations. And the second goal would be to actually find the regions in the image that represent individual objects. So let's see how this would go. First of all, humans have no difficulty doing it. And our goal is to have Čapek do the same without familiarity of learning. So this is example with one object. It looks like a simple example, but you realize that with this dance floor, the specular reflections and shadows, this is actually not a very easy problem. But in the case of one object, our Čapek was able to find it. And if I remember the labeling correctly, the red square here is the ground truth. So the actual position, size, and orientation of the object in the top view, and the green one is the robot's estimation of the object. So we can add a second object. It looks, so in this representation on the bottom left, the robot is standing somewhere here, and standing somewhere here just looking at the scene, and this is the floor plan of what it sees. So this object is here, this one is closer. Then we have another one, and now this third object is actually partially occluded by this one. Now it's interesting to note two quite remarkable things. Namely, even though our robot and you can only see the visible parts of this front object, the robot actually knows where the object ends on the back invisible side. This can be done by using our predilections of symmetry plus some assumptions about the direction of gravity and orientation of the horizontal ground. And furthermore, even though there is no direct visual evidence about the amount of empty space between those two objects, the robot actually can estimate the amount of empty space between them, which will be essential in planning any meaningful navigation if there is need to do it. I think this is what I just said. And we humans actually do it all the time. So you don't really have to have direct sensory data in order to see what's going on. This was true with recovering the back part of the shape, and this is true with recovering the back invisible surfaces of an object and invisible spaces in the scene. So let's add a few more objects. We can add the fourth one, the fifth one, the sixth one. The sixth one is, again, the bottom is almost completely occluded. The seventh one, the eighth one. Now, this one is quite challenging, right? Without actually knowing that it is there, it may be difficult to see the stand behind this chair. The chair is partially transparent. This is how you can see that it is there. The reconstruction is not perfect, but the data is actually less and less reliable. We can add another object and two more objects. So by now, this is quite a complex scene, yet there is a way to produce the interpretation of the scene, namely to figure out what the objects are and where they are. Can this work with dynamic scenes? We didn't do a lot of experiments, but this would be a quick example. We asked people to wander around a lab, and the green ellipses on the left represent how well the robot could detect the people, and the dots on the right represent the centers of people, and most of the time the robot can count the number of moving objects and can track them. So we are actually getting close to some concluding statements. We have 2 or 3 more slides. What you have seen so far may be the very best way to solve the figure ground problem and to perform 3-dimensional recoveries. Recall that these problems seemed insoluble when first brought up. If ours is the best way to solve them, by ours I mean the way it works in our brain, in our mind, there is no need to try to develop a robot with superhuman seeing abilities. There may just be no way to do it better than what humans do. Note that making Čapek's vision work like ours was essential for actually formulating a theory of human 3-dimensional vision and understanding what's going on. So, summary. Humans, among other animals, are said to be the most intelligent. Some of them can be even called super smart. The only meaningful way to study human intelligence is actually by emulating it. So far, we have barely scratched the surface in our attempt to understand the human mind and how it is used in the biological and physical world. Developing intelligent robots which emulate us can provide a powerful strategy and tool for achieving this goal scientifically. Let's use it. Conclusions. We should not be afraid of super intelligent robots. They are neither here nor even near. What is possible and could be dangerous is to build and use robots that are not so intelligent. We need to keep perfecting robots to bring their intelligence closer to ours. They are very far away now. This may prove to be the best, perhaps even the only way to understand and explain why the human mind works so well. If you want to find more information about how the human visual system works, you can check our recent book on emulating human vision. Thank you very much, and we have a few minutes for questions.
How important is binocular vision to solving for humans, to solve the 3D problem, compared to like some of the priors?
So this is still a topic of research. We know that if you close one eye, you actually can do pretty much all the tasks. We know that there are some famous baseball players who are blind on one eye. And if you had a colleague in your workplace who is blind on one eye, unless he tells you that he's blind on one eye, you wouldn't know it. One way to realize how this can be done is that if you are blind on one eye, but you move your head a little bit, you are now simulating binocular vision because you are placing one eye in 2 different spaces in space. So between the motion and binocular, you can do a lot. What is interesting, how much actually can be done even without binocular and without motion. But the evidence that we have, and is described in our papers, we are able to show that there are cases where binocular vision or motion gives you quite substantial improvement in 3-dimensional recovery. But it is almost never the situation that you see an object or not. It is the precision with which you can do it. So binocular vision is important, but it's less important than is typically claimed.
Any other questions?
Yes?
You said in the example with the tables and detecting them in the room that you used the orientation of gravity to some extent to aid in that. Could you elaborate on how you use that?
Yeah, so if in the typical conditions, the objects in the presence of gravity, then they rest on the ground. And this happens to be a very useful, either if you will, piece of information or the assumption. One way to see what's going on is that once you detect a region in the retinal image, single image, which contains an object, if you know your height, the height of your eye above the floor, and you know that the floor is horizontal, namely orthogonal to the gravity, there is just simple trigonometry to take a line emanating in the center of perspective projection of the eye or camera, going through this region in the image, and you extend it until it hits the floor that you just estimated, and you know the position of the object, its size on the floor. So this, if you try to perform this recovery of sizes and positions of objects, but you allow them to float in the air, it's much more difficult. And in fact, humans are not very good at it. There is quite a lot of research showing that if you have objects hanging from the ceiling and you don't see the ropes on which they are hanging, we are quite bad in judging distances, sizes, or angles of the configurations. Yes?
So your whole perception is based on mimicking what humans see and humans perceive. But I think we can develop robots with more capabilities than humans that may or may not increase the capabilities of what humans do. For example, there are many advanced techniques with laser scans or infrared, etc. Robots robots do not have that perception system in their mind, but they can use other tools like the infrared to have the scan of the room and have there are recent papers which are doing real-time RGB reconstruction of everything. So instead of trying to perceive what it is in their mind, if they can do a 3D reconstruction on the fly, which we cannot do that accurately, actually. But they can do that reconstruction and they can perceive the scene better.
Yeah, thanks. So yeah, there are a number of sensors that you can use. Infrared, like Kinect, can give you quite precise reconstruction of surfaces, but it only would work inside because outside there is too much infrared coming from the sun. But then you can use laser sensors. They can measure the distances of visible surfaces. So there are those tools, and there is quite intense research of trying to produce devices which would be as good as possible. It is hard to predict how far it's going to go. At this point, those all sensors put together, they cannot produce the 3D recovery, which is as good as what humans perceive, unless you allow in the room several dozen cameras and you calibrate the entire system. Then you start approaching the reconstruction that what humans do. Still, they typically don't recover the back sides of the objects. So if you go to the conferences on computer and human vision, or you read papers, as of today, the assumption is that human vision is way better than almost anything that exists out there. Now, there may be particular applications, like if you want to do some micro manipulations, then the human visual acuity may not be good enough. Microscope can help. So there would be a few applications where you can do better than what humans do. But in natural conditions with natural objects, the way we see, and quite possibly the way many animals like cats, monkeys, birds see, is much better than what's out there. So the goal of this research is to do both, is to keep studying human vision and checking how much we can improve the artificial systems. 5 minutes?
Any other questions?
So you're talking about this sphere hanging from the ceiling. If you couldn't see the rope, if you create your own limit to the position that you can see, will that help your perception?
No. This was actually, there's really tons of papers trying all configurations. In fact, the assumption was that scientific studies should try to be as clean as possible. So they were typically trying to remove the pieces of information that could be used like floor. But the moment you start producing those artificial arrangements, the errors are quite big, and the system is very sloppy.
So limiting the precision of the robot?
So we would, it's from the computational point of view, if you cannot use symmetry, compactness, if you cannot use gravity, you don't know your own height, then there's no magic. Robot would just have to rely on brute force stereo reconstruction. And we know that with the distance between the cameras of 6 to 10 centimeters, you will never reconstruct the depth reliably. So it will be as poor as we are under those conditions.
Anyone else?
Here we have a question in front.
So, one thing that I've heard with research done with developing the Oculus Rift was that they had some trouble testing it on women, and what they discovered is that men and women perceive depth very differently. From what I understand, a male brain relies more heavily on parallax, whereas a female brain relies more heavily on changing light. To me, this suggests two different ways of recognizing moving objects in space, and I was wondering if there are two different ways of recognizing moving objects in space, wouldn't that just suggest that there are other ways that computer vision can be achieved at the human level that is not anything like the way that humans perceive
What was
space?
the name of the project? Or
The Oculus Rift.
Mm-hmm. So yeah, there has been a lot of excitement in trying to figure out gender differences in almost anything, including visual perception. When I teach a class on perception, I say all humans see the same way, period. So in my lab, we were never able to detect any gender differences. And if you scrutinize the work that is being published, then you see that the evidence which is published is either extremely weak or the statistics actually makes things difficult to figure out. So we know that if you ask about gender differences, we know that about 10% of male population has some problems with color vision, and in female population, this almost never happens. There is an easy explanation of this, that the color part of the coding is sitting in the X chromosome. So if you have X and Y and X is broken, you will have color problems. But these are relatively low level and simple cases due to some issues related to the genetics. But as long as you have normal visual system, there is no reliable data that would indicate any gender differences in perception of motion, shape, structure, distance. We all see things the same way. Now, we are always open to see some new results, but it is surprisingly difficult to find individual differences in perception of three-dimensional space. And I would say that there are actually no gender differences when it comes to this. So it's just you have to, when you read the papers, you have to figure out how good the methodology was, how big the differences which are detected are, and how good the statistics is. And in fact, the last 10 years of reanalyzing what was happening in our sciences, we know that there were a number of spurious effects published, and the spurious effect was caused only by the bad statistics that we have been using. So now the field is shifting to the new way of doing hypothesis testing, and many of those effects are going away. So one should be careful in making inferences based on a handful of studies.
Thank you very much.
Thank you.